He loves open source and also organizes the PyData meetup in Zurich. So if you attend this meetup, which some of you may, you will already know him. Yes, and he will talk about causal machine learning, and I'm glad I pronounced it correctly because I always read casual machine learning. And yeah. Okay, so the stage is yours.
Thank you very much.
Thank you.
Good morning, everybody. My name is Kevin. This is Francesc. And we'd like to show you how one can use the meta-learners library to learn from experiments. And to get us started, I would like to think about this duality of kinds of growths. So on the right-hand side, we see a skeleton made of human bones, right? And these bones are rather unresponsive to stimuli. You can think of them as more or less fixed. You won't train them all that much. On the left-hand side, though, we see muscles. And muscles are very responsive to stimuli, right? You can easily make them grow faster, stronger, bigger. And this duality, I would like to use as an analogy for what psychologists call learning mindsets. So learning mindsets basically just mean how one approaches the fact of learning, how one thinks of acquiring intelligence or intellectual aptitude. And these psychologists tend to think of two different kinds of learning mindsets. The one is called the fixed learning mindset, and that's much like the skeleton or the bones we see on the right-hand side. It presumes that intelligence and intellectual aptitude are fixed traits given at birth. On the other hand, the growth learning mindset is much more like a muscle. It presumes that intelligence and performance at school are things that can be enhanced with hard work, with effective strategies, and with the support from the right people. I think it's rather natural that we would want our students to rather follow the growth learning mindset, to believe in themselves that they can improve. Now, I think as soon as we set out this goal, I think it would be a wholesome idea that just every student would be coached in that regard, would be told that they can develop, that they can work on themselves. However, coaching is expensive, and we live in a budget-constrained world. So if we now presume that we have a limited amount of coaching hours for this growth learning mindset, naturally we would ask the question of a policy, namely which students should be coached in order to optimize or maximize some goal of ours, which could, for instance, be the cumulative gain in grade point average, basically your average at school. And this question we will try to answer with an experiment. And this experiment is called the National Study of Learning Mindsets. It was conducted in 2019 by a group of North American universities and research institutes. And what happened there was that they chose approximately 70 high schools across the United States. Now, from each of these high schools, the students were brought together and were basically defined as to be the experiment population. So these were the experiment units, if you will. Now, the experiment itself was a randomized control trial. So for every student, every experiment unit, there was a coin flip. Heads would indicate that this particular student would get coaching in terms of the growth learning mindset, and tails would mean that they would not get any coaching. This intervention or this treatment happened in 9th grade, respectively. Now, in order to come to conclusions as to what this coaching leads to, there was an outcome. And this outcome was basically a grade point average, GPA, of their school results months or years after the intervention. So this is kind of the rough experiment setup. And a bit more formally, we can think of this data that was gathered in this experiment as a set of triplets. And now every triplet represents an individual student. And it is a triplet because we have different kinds of information. On the one hand, we have the so-called covariates. You can also think of them as features. They typically describe properties of a student or the school that a student attended. We would also refer to that as axi. Secondly, we have the treatment assignments. These are basically just indicators whether a given student at hand received the coaching or did not receive the coaching. The last kind of information we have are the outcomes. And in our case, these are just GPAs, so like a real scalar, as we said before, months after the treatment. So this is, more formally speaking, the data we have at hand. And in a bit more detail, we have approximately 10,000 students who took part in this, to give you a ballpark idea of what we're talking about. And we said before there was a randomized control trial So the assignment was independent of the covariates, but it was a biased coin. So approximately a third of the students did receive the coaching and 2/3 did not receive coaching. As you said before, this experiment was part of this national study of learning mindsets, of which the insights were published in Nature in September of 2019. The data we will use, though, is an anonymized version of that same data provided by Athey and Wager from Stanford University. They took care of some anonymization transformations, and in particular, they also transformed all continuous features and the outcome to follow a standard normal. Now, to make this a bit more tangible, here we have an excerpt of our data. And in this table, every row corresponds to a student. And we can see that we have a whole lot of these covariates that describe the student. So for instance, the ethnicity or the gender, which are categorical variables. They have numeric values, but they're not supposed to be interpreted in an ordinal or numerical fashion. As we also said before, we also have information on the school that a specific student went to, such as the school poverty or the school size, which are regular numerical features. We don't only have the covariates, but we have these two other elements too, namely the treatment assignments, which we can see here, which are just binary indicators as to whether a given student received coaching or not. And lastly, the achievement score, which is the GPA after a couple of months, but then transformed to follow a standard norm. Now, as is always the case, things start off by loading the data. And this anonymized data set is conveniently provided and publicly available in CSV format, so we'll just load it as a pandas data frame. Now, the next thing we do is to explicitly list all of our covariates, which we want to be interpreted as categoricals, so not as numerical or ordinal features. And so now you might be used to then, as a next step, do some one-hot encoding or the like as a next step, and this is not what we will do. What we will do, though, is to cast these covariates or these columns into pandas category D types. So we will not one-hot encode. The reason why we're doing this is that we want to leverage the capabilities of certain machine learning models, which have native features for categoricals. And this we can see here, simple decision trees. Various decision tree implementations have native support for categoricals, among those LightGBM, CatBoost, and XGBoost. And on the right-hand side, we see a simple decision tree that relies only on one feature, the school size. The school size, naturally speaking, is a numerical. Therefore, the operators that we find in the nodes of the decision tree are just arithmetic comparisons. They're greater or equal. Now, we have on the left-hand side a different kind of decision tree, one that relies on a categorical feature, the ethnicity. And what we can see here is that the operations inside of the nodes are no longer arithmetic comparisons, but rather subset relationships. So the decision tree understands that ethnicity can have several values, but that these are not to be treated as numbers necessarily. So this feature we want to use. And we said before that we have these outcomes, these standard normal GPAs. And on the right-hand side, we can see a histogram of that in gray, and it looks about fine. It is more or less centered at 0, looks more or less symmetric. Most of the mass is between -1 and 1. Now, if we split up these outcomes into students who did receive coaching in green and students who did not receive coaching in red, visually speaking, we get the sense that coaching is a good idea because we do not have any confounding here. There was a randomized control trial. This is only visual and only on average, though. So now I talked about this data set, and what do we actually want to do with it? Well, remember, our original question was, which students should be coached? Because we presume that we have typically a finite budget of coaching hours to distribute. And this question we will reduce to a slightly different question, which is, how much would a student like student I profit from a growth mindset coaching? And so once we have figured out how much the GPA of a given student improves by giving them coaching, we can easily decide the former question by just saying, okay, we'll give it to the top K%, something like that. And to formalize this a little more, we stick with question B for a moment, and we use a formalism from the field of causal inference, which is called the conditional average treatment effect, also abbreviated as CATE, to really just represent the question we're asking in math. And conditional average treatment effect basically consists of 3 components: conditional, average, and treatment effect. Let's start with the treatment effect. Treatment effect basically just means that we're comparing two different outcomes in two different worlds. So I think this is rather intuitive in the sense that we ask the question of, for a given student, what would have been their GPA had they received coaching? And what would have been their GPA had they not received coaching? And compare these two implications of causal situations. And since our outcome is just a real, is a scalar, we can just do this comparison with the subtraction. The second component is the average. And this is just manifested in that we compute, or we're trying to estimate an expected value. Now, lastly, we see the component of conditional in our conditional average treatment effect. And this means that our expectation is not with respect to the entire student population, but rather with respect to students who have the same or very similar covariates. And so this means that our interpretation of the CATE is not on average, how much does the GPA raise thanks to coaching, but rather the interpretation is, in expectation, how much does the GPA increase thanks to coaching for someone who is like student I, so say like Anne. So we take care and we are sensible to this heterogeneity in the treatment effects. Now, once we have figured out how to estimate this conditional average treatment effect, we can go up again to the original question, question A, which students should be coached, and define a very trivial policy, pi. Now, this policy pi is again heterogeneous, is sensitive to the covariates xi. And its decision as to whether a student receives coaching, 1, or does not receive coaching, 0, is very trivial if we have these CATE estimates. Because we can just say, well, if the expected gain of the coaching is above a certain threshold, that is a function of our budget, we will give coaching. If it is below that threshold, we will not give coaching. And that way, we treat the top K% of the students. So this is all nice and well, but this, of course, bears the question of where do we get these estimates for these conditional average treatment effects from? And our answer to that question are meta-learners. Meta-learners, unfortunately, were not invented by Francesc and I. We merely implemented them. And meta-learners are a family of CATE models. So models that estimate this quantity, this estimate that we saw on the previous slide. And what's special about them is that they have a very modular, composable structure. So here, the larger geometrical shape is supposed to represent the meta-learner, and these smaller triangles inside of it are supposed to represent arbitrary supervised learning models, so regular machine learning models. There's many of those inside a meta-learner. And as we said before, we had 3 different kinds of information in our experiment data set, and this happens to be exactly the kind of information that a meta-learner consumes. So firstly, we have the treatment assignments, whether a student did receive coaching or not. Secondly, we have the covariates, the properties of the student and the school. And lastly, we have the outcomes, the GPAs of every respective student months after the intervention. What these meta-learners spit out are exactly the quantity that we talked about. These CATE estimates for every single student that took part in the experiment. In particular, they yield us estimates with very favorable statistical properties. Now, as per usual, we don't only get the estimates, but implicitly we also learn a function, tau hat, that we could in the future apply to unseen data. Now, Francesc is going to make it more tangible as to what this looks like in code.
Hi, thanks. So yeah, now we, as Kevin explained, we implemented a library for doing this. And the first thing that I'm going to show you is how to create these meta-learners and how to be able to train them. And the first thing that you would need to do with any regular Python library is just the regular imports. In this case, we're going to use an R learner, which is a type of meta-learners. We have multiple of them implemented, but for example, we're just going to show this one. And then, as Kevin explained, we have multiple base models inside the meta-learner, and these base models are regular standard machine learning models that you can use, that you have probably used, such as LightGBM trees. And in this case, we're going to use regressor and classifiers from LightGBM. And then to instantiate our meta-learner, we just need to pass the factories for each of the base models. And in this case, for the nuisance and the treatment model, we're going to use LightGBM regressors. And for the propensity model, we're going to use a classifier. Then we have a couple more parameters which are mandatory. In this case, we have the is classification, which means whether our outcome is a classification outcome or a regression.
we have the outcome is a GPA, so it's a real value. So in this case, it's false. And at the end, we have the number of variants, which is just how many treatment options we have. In our case, we have 2 because the student can either receive coaching or not receive coaching, but the library supports any number of discrete treatment variants. So you could have 10 treatment variants or more. And then we just need to call fit with the data. And this probably reminds you of any scikit-learn model or similar, which is one idea that we had to try to implement in the library was to make it easy for users that know already these machine learning models to make it easy for them to use it. But the main difference here is besides having to pass the X, which are the feature, and the Y, which are the outcome column, which is the GPA in our case, we also need to pass the W, which is the treatment. This is because meta-learners receive all three inputs, and they need all of them to compute our K estimates. And then we can just call predict, as you would do with a scikit-learn model, and just this meta-learner provides us with some K estimates of our data. And we did the first experiment, and we saw this plot. And one of the first things that were weird for us was the fact that there are many students which would not benefit, and it would be discouraged for them to receive coaching. So for us, that was a little bit weird, but because as we saw in the previous plot, most of the treatment effect was positive, looked positive for most of the students. So this was a little bit weird for us. And we were a little bit struggling to understand what was happening here. And the first idea that came to our mind was to do hyperparameter optimization. So if you've used machine learning models, you know that hyperparameter tuning has a really high impact on the prediction and how good the models are. And tuning these parameters is really important to have good models. So there are some works in recent papers that show that this also happens in meta-learners, which is intuitive because at the end, if we have these base models change their predictions due to the hyperparameters, then the final K estimate is going to also change a lot. But the main difference that we have here with regular machine learning is that we have 3 levels. So the first level is the meta-learner architecture, meaning whether we're going to use an R-learner, which is the one that I showed before, or a T-learner or an X-learner, or any of the ones that we have implemented. The second level is the model to choose per base estimator. There's one thing that we realize that's also usually important. We are using light GVM trees, but we can use any scikit-learn models, basically anything that implements fit and predict. And in this case, we could use linear regression or discriminant analysis or anything similar. And finally, the actual hyperparameters of each of these base models, which are the ones that you're probably used to it, such as the number of trees in the case of boosting trees, or the regularization weight, or anything similar. And then we decided to perform a grid search to evaluate different models and parameters. And we wanted to test a light GVM regressor. In this case, we have an R-learner and we have 3 base models. And for the outcome model, which is this one here, we wanted to test an light GVM regressor, but we wanted to try different number of trees and also different number of max depth. Then for the propensity model, we also wanted to just use a light GVM classifier because according to what we've been using, they usually work well with tabular data, but we wanted to have less trees, but we also test a couple number different, and also we wanted to test also different numbers for the maximum depth, and the same for the outcome model, which in this case, we're just going to use a light GVM regressor, but with also multiple number of trees and max depth. And for this, we have some helper functions because, as you can quickly imagine, this grid kind of explodes really quickly, and it's really hard to keep track which experiment you run and which not. So we have to define our grids for this grid search, and in this case, for the base learner grid, we just need to pass the different type of models, which are just regressor and classifier, like GVM trees. But for the parameter grid, we want to test different parameters for just these base models. And in this case, for the light GVM regressor of the outcome model, we want to test 25 and 50 and 100, as shown before in the previous image. And now we would just be able to pass all this to an object called meta-learner grid search. We just need to pass the type of meta-learner, which is an R-learner, and also the different parameters that we're going to use, and just the grids that we defined before. And we would just need call fit with some part of our data as a train set and some part as a validation. Then this would give us some results, which would give all the results for all of the combination of the hyperparameters. And as we can see, we have different measures for each of the models. But the most important things are the fact that we have the loss of each of these base models. In this case, we have the loss of the propensity model and the outcome model and the treatment model. We also have an R loss, which is a measure of how good our Kate estimates are. This is possible because we're using an R learner. And then we decided to use our test R loss in the test data set and choose the best model, which was with the lowest R loss, which was this one here. With this loss of 0.81. And with this, we fitted our meta learner. We use this meta learner, and we can see that our Kate estimates are much more concentrated in the middle. One thing that's important is that much less students are below 0, which made more sense. At the end, it's a little. It will still have some negative, but we know that the data is a little bit noisy, so this was one of the reasons. And then we could trust much more these Kate estimates. Then, as was explained in the previous talk, some models are really treated just as a black box, and it's really hard to interpret them. And there are some techniques to do that, such as Lime and SHAP, and we have some nice integrations with our library. And for example, we can work with SHAP values, and with just 4 lines of code, which is really simple, we can just generate SHAP values showing which features are the most important and the less important for our model. And we can really see that school ID, in our case, is a really important feature. This makes sense because at the end, the student's mindset probably depends a lot on which school they come from and how they also work with their colleagues. And this was one of the things that were according to findings from the previous papers. Also, ethnicity has high impact, and so on. But now we want to see how good are we actually doing and how good our Kate estimates are and how much we can benefit from these Kate estimates. So we can define a policy value. This is a measure that defines how good our policy is. And as Kevin explained before, we can define a policy which just treats the most promising students, the ones with the highest Kate estimates, and we can measure the average GPA or the average outcome of applying this policy, and this is defined as the policy value. And we can do this plot then, which shows how much we benefit from our Kate estimates. And in this plot, on the x-axis, we have the number of treated students, and on the y-axis, we have this policy value that we define. And then we have 2 lines. The orange line is just a uniformly random policy, meaning that we just choose, for example, in this point here, we just choose around 3,000 students at random. And this would give around an average of minus 0.01. But using our Kate estimates, we can increase a little bit this policy value to 0.03. These numbers probably don't mean a lot to you because, as Kevin explained, the values are standardized to a regular normal, but we converted them to what does it mean in average GPA. And this means that, for example, in this case, we would increase around 0.05 the average GPA of all the students. And this is useful because in this way we can define how much we want the GPA. For example, in the student, we want how much is worth each point of the GPA, and we could define how much is worth 1 hour of coaching, and we could see the optimal point of this curve how much students we need to coach to get that much GPA increase. And yeah, that's right. It's going to finish.
So if you'd like to work on all things open source or all things causal inference or other things, please consider reaching out to Quantco, where we have done this work at. You can find more information on quantco.com. You can talk to Francesc and I. Please reach out. This is a snapshot of some of the roles we currently have open across the fields of data science, engineering, and deep learning. We're hiring in Europe, but also in North America. We're very flexible with many of the details. So please reach out if you're interested. Thank you very much for your attention. If you have any suggestions, ideas, complaints, please let us know, either in person or via GitHub. We're happy for any feedback we can get, and hope you have a great rest of the day.
All right, thanks a lot, two of you. Are there questions in the audience? I see one in front here and two in the back, one there. Okay, so 4 questions. So let's start with the one in front here.
Thank you. Is your policy, is your system being used in policy making? Is it being used like for politicians, decision makers, in education, or is it more academic?
So we built this at our company because we needed it. It's really because we needed it at work. We don't really do governmental policy advisory, but rather we collaborate with e-commerces and with insurances to improve their decision-making in many regards. And they have lots of these causal decision-making questions as to whose claim should be investigated by a person and whose claim should be investigated by only, a piece of code, basically. Who should get a voucher, who should not get a voucher. There's lots of these very similar treatment decisions or policy decisions to be made, and that's where we apply them. But we know of researchers who are currently using the library as well in, say, biochemistry.
All right, there were questions in the back, right?
Thanks, really nice talk. I just have a question about the randomization. Is it per person or per school?
Per person.
And then I have a follow-up. I had the feeling that you may have a problem with a spillover effect. Because if I have a friend that's like pretty similar covariates than me, I would look at him and what he learns from the training and also adopt, and then like the treatment effect would like be underestimated.
Absolutely. Absolutely. And I think this is like, fortunately, the bias is in the right direction, right? So we're not sort of over-promising what the effect of coaching would be, but rather maybe underestimating it. But I totally see your point. There is some spillage. I think in order to mitigate that as much as possible, the mentoring sessions were really conducted outside of school. So it wasn't that just some people stayed in the classroom and others didn't, but rather they took place online. So it really tried to separate it as much as possible from the regular school days and only had these sessions online with very selected one-on-one sessions. But I totally see your point.
And just a quick follow-up. I mean, I fully agree that in the end, the average cost treatment effect be conservative, but I see more the problem if you try to assign treatments based on covariates. Because there could be that it's like, that you kind of select the wrong people because the bias would be unequally distributed. We can talk later about
Yeah, sure. I'm happy to do that. Happy to do that.
All right, on the left. Yeah.
Yeah, I really love your concept, actually. I feel it. At least I feel the potential outcome of it. I have a question because, like, when you coach overall someone, I see the point that you don't really take into account that some people are stronger in certain topics and in certain not. For example, if you would coach me in languages, that would be horrible because I can't explain it binary. If you would coach me in math or geometry, or back then, you would be better off and I would have a stronger learning curve. Mm-hmm. And I don't know if your data also takes this into account, that people actually need to be supported in a different way.
Right. So we only looked at the overall GPA now as an outcome. I think in the Nature paper, they look at a whole different kinds of outcomes. So also just GPA in like STEM, but then also how many of these students actually ended up going to college. So they do differentiate with respect to different outcomes. The treatment itself, I think, was really meant to be as agnostic as possible. So I think the coaching was really more about the general idea that you can improve yourself in terms of learning. That if you do hard work and if you have like a good study plan and if you have, I don't know, the right friends who don't do as many drugs, that you will improve at school. I think that was more the general idea and not so much like really helping in the respective domains.
I get that, but in older age, you also make a decision, what do you want to further study or where do you want to work? and that's normally topic specific, right?
I see.
So therefore, my personal opinion,
Yeah,
I would like that like also the topic needs to be considered.
I understand.
All right, there was a question in the back, right? Yeah.
Yes. Thank you for your talk. I couldn't fully follow the meta learner. Why do we need 3 models? And is this W, what's the difference to an input feature X? Not just an input feature?
Like, you mean, like, why do we need different models inside the meta learner, or?
Yes, why is this W what makes it different from a covariant?
Yeah, the meta learner at the end, it's like there are different meta learners and different techniques. And for example, one of the most simple one would be like an S learner, which is basically just adding the feature of the treatment. You would just add it and just feed it to a regular machine learning model, and you would just add it as a feature, like the treatment, which treatment they received. But there are some nice properties of better meta learners, and for example, this is an R learner, which has three base models. And at the end, they regress different things. Like there's one model which regress the outcome based on the covariates, and one model which regress the treatment based on the covariates. And they combine this using some formulas to reduce the bias of this of the outcome assignment and different biases at the end. I don't know.
So maybe to give a concrete counterexample, let's assume we do it that way, that we basically just treat the treatment assignment as another covariate. I think this could really badly fail if we don't have a randomized control trial. So what's special about meta-learners is that they're not sort of constrained to randomized control trials, but they can also be applied to observational data. And in observational data, you might have very strong confounding between the treatment assignment and the covariates. And in that case, you really want a special kind of machinery that tries to debias this confounding that's taking place in order to actually come up with a causal estimate.
So by debias, you mean separating cause from just covariation?
Yeah, exactly.
All right. Thanks a lot. Yeah,